Yeah, so how many of you have heard about data-centric AI? I guess like today, many of you have probably heard the term, right? We seem to be getting a lot of hype in this area. Articles coming out in publications like Forbes, leading machine learning researchers and practitioners like Andrew Ng, saying that people are spending so much time, like 80% of people whose job is ostensibly ML are actually just doing data preparation, and that this data quality has a huge impact on any downstream applications, whether it's training machine learning models or anything else like doing data analytics or business intelligence. And there are articles in the Harvard Business Review saying that this bad data is costing us $3 trillion a year. But the good news is that this problem is actually solvable. And in the past, I think people have been very focused on the machine learning models, right? The modeling side was always, or has been more exciting in the past. And you didn't hear people talk about data as much. But yeah, there's some interesting stuff going on here. Like when you train machine learning models on bad data, they don't do very well, right? And clearly there's something important happening with the data, and models are actually capable of fitting totally random, like useless data. And there's a result from researchers in 2017 saying that you can take a ImageNet model and just fit it to the ImageNet data set where you've replaced all the labels with random labels. They're just like totally capable of memorizing that entire data set. So something interesting going on there. Yeah, maybe hints at the importance of data quality for machine learning and other applications. And leading companies in the ML/AI space have recognized this. It's like OpenAI has talked a lot about the importance of data quality. For example, in the context of DALL-E 2, their image generation model, so they've talked about how training data shapes the capability of any learned model. And so even the basic data filtering can be a powerful tool for limiting undesirable model capabilities. And they even talked about how they prioritize filtering out bad data over leaving in all the good data. Like it's actually better to have a little bit less data and potentially throw out some okay examples than have bad data in the data set. Because you can always fine tune the model to improve it later, but it's once your models learn something incorrect, we don't really know how to effectively make the model forget that incorrect information. And for this image generation models, some of the problems that they had to deal with for curating that data set included things like duplicated images or just low quality, low information images, and even mislabeled data. Like here, they were trying to make an image generation model, which given a text input can generate an image, like give me a picture of a red car. And then if you train such a model on incorrectly labeled data, it's not gonna work very well, right? So I talked about how if you have, say, an image of a plane that's labeled car, then this model is going to learn a bad representation. And then when the user goes and tries to generate a car, well, it's seen this text car paired with this picture of what is obviously a plane. And so you might get a model that's not robust or does the wrong thing. And so the reliability and performance of these machine learning models is going to depend on the quality of that training data. And in fact, researchers from OpenAI, one researcher from OpenAI said that the it in AI models is the data set. With some of these large generative language models recently, it appears to be the case that actually the details of the model architecture and training like optimization parameters and things like that don't matter all that much. Like if you train a sufficiently large model with enough capacity and train it until convergence, no matter kind of what architecture you change, what little tweaks you make, you'll kind of get to the same point. It's actually just dependent on the data. So like when we talk about LLMs like ChatGPT versus Claude, we're not really talking about the model architecture. It's really just about the data and like the learned representation of that data. And it's not just OpenAI that's recognized this. Other top companies talk about how data quality is super important. So like Andrej Karpathy, for example, the former Tesla director of AI, talked about how early in his career when he was an academic, he would spend all his time thinking about models and algorithms. But in practice, like when he went to Tesla and started to work on this really tough problem of making a self-driving car that works only based on computer vision rather than using sophisticated sensors like LiDAR and other things, the focus was really on the data and data quality. And they spent a lot of their time and money on curating high quality data in what they call this Tesla data engine. To make it a little bit more concrete, like what I mean when I say data quality issues, here's one example of a type of issue: label errors in supervised learning training data. And so here are some real errors we've found using some of the tools that CleanLab has developed in some highly curated, like gold standard academic data sets. Maybe many of you have heard of these data sets like MNIST and ImageNet. So MNIST is this classical benchmark data set. That's a handwritten digit recognition set created by Jan LeCun. And yeah, in that data set, we found examples like this image of a 3 labeled a 5, or an image of what's obviously a 7 labeled a 4. And yeah, similar problems occur in ImageNet. This is a larger image classification data set, 1,000-way image classification. And yeah, we can see tons of incorrectly labeled data in here as well. I'll give this picture of what's obviously a lion labeled monkey, a picture of a hamster or something labeled a beaver, a bee labeled an ant, and a very lazy looking bear, but it's not a sloth, it's still a bear. And we did some research and found that these errors, even in these gold standard academic data sets, are quite prevalent. So we looked at a bunch of different data modalities and in a bunch of these academic data sets, looking at a bunch of image data sets, some text data sets like 20 News and IMDb and the Amazon review set, and audio data sets as well. And just found that pretty universally, we can automatically find a lot of data issues and actually validate them with by having humans check the issues, and found that like indeed there's a lot of error here. So it's actually really tough to curate these high quality data sets. What's kind of interesting was when we did some of this early research, people were quite excited about the results, talking about how the foundations of AI are riddled with errors. Like, why was it surprising that we could find a bunch of these issues? Like, surely people would have noticed these issues given that these data sets have been around for many years. Like ImageNet's been around for what, more than a decade now, MNIST for a couple decades. But I think one of the reasons why this was surprising and interesting was, well, we found a bunch of errors, and it's hard to do this without a systematic and automated approach to data issue finding. I think people had run across these things, like grad students working on trying to develop a better ML model on ImageNet, they end up looking at some of the training data and might notice something wrong. But what's really interesting is, there's a large fraction of errors in this data set. Very hard to do that without a systematic approach. There are also some interesting implications in terms of using erroneous data to test machine learning. So like if you're, say, training a bunch of ML models and trying to decide which one you want to use in production, and you're doing so by benchmarking it on your test data. Well, if your test data is wrong, you're like grading your model according to an incorrect rubric, well, you might end up choosing the wrong model. And we actually found that we could train multiple ML models, find that A is better than B on a particular test set. But if we actually improved the quality of the test set, it would flip the results, like model B is better than model A. And so that was kind of interesting, leading to this potential issue that we might be doing benchmarking not quite correctly on these gold standard academic data sets. So anyway, going back to this data-centric AI topic, so what is data-centric AI? Isn't it just like, what is the difference between data-centric AI and machine learning? So in traditional machine learning, the process looks roughly like this: that you have some raw data set, maybe you format it to be amenable to training machine learning models on the data, and then you might do some manual data quality stuff. You remove rows that have nulls in it or things like that, and use other ad hoc approaches to improve data quality to some degree. But the majority of the focus is on better modeling. So you'll train some initial ML model, but then after that, keep tinkering with the model, explore different loss functions, regularizers, optimizers, hyperparameters, neural network architectures, and so on. But the difference is in data-centric AI, there's this other step that comes in between where you use the initial ML model you train on the data set, which is actually really useful in that it learns some representation of your data set. You can use that model to actually improve the data quality and do so using techniques that are automated and systematic, rather than based on intuition and being ad hoc techniques. And only after improving the data quality do you do the model improvement side of things. So you first improve the data, and then you can even stop there. If you have a high quality data set, you can even just train your original ML model on the improved data, and that'll give you a performance boost without even having to tinker with the model. But of course, after that, you can continue working on the model side and get an even better model to further improve performance on that data set. So in summary, data-centric AI is all about systematic approaches to improving data quality. And so in this talk, I'm going to cover a bunch of different types of data issues we've looked at and different algorithms we've developed to address them. And most of what I'm covering in this talk is released in this open source package, github.com/cleanlab/cleanlab, which is our data-centric AI package for dealing with various types of data quality issues. And at the end of the talk, I'll talk a little bit about CleanLab Studio, which is a SaaS tool we've developed that incorporates and builds on top of these algorithms and does a little bit more than what we do in the open source. So the CleanLab open source package works with most data modalities. A lot of the algorithms we've developed are data modality agnostic, because so they work with like image data or text data or audio data or tabular data or whatever type of data you have. As long as you can train an ML model on your data, you can plug in the model into CleanLab and it works with your data type. And it works with a whole bunch of different modeling frameworks. And using the library is actually pretty easy to detect a lot of different types of data issues. It really just requires a couple lines of code. And the key idea here is you pass in some key information that's learned by your trained ML model, where you train an ML model on your original noisy data set. And so you supply CleanLab with feature embeddings if you have them from your model and out of sample predicted probabilities. And based on that, we can provide a whole lot of different, flag a whole lot of different data issues. And so I'm going to stress a lot of image examples in this talk because they're very intuitively understandable. But some examples of some of the types of issues we can automatically find using the approaches we've developed are things like identifying nearly duplicated images in a training data set that say might contribute to poor performance in a, say, generative image task. We can find mislabeled data in a data set. We can find outliers. We can find non-IAD images and more. And of course, just again, it's not only image issues. We can find issues in text data or any other data modality. Again, just plug in your own model and it works. So here are some, I think these are data points from the banking intent data set. Customer service request comes in, we want to classify it as a one of a number of categories. And so here too, we can find label issues or ambiguous examples or this bogus data like this, this outlier here. So the first issue type I'll talk about briefly is detecting outliers. And here we have a really simple approach that works quite well. So we found that with good embeddings, and these days we have really great pre-trained models where we can easily take an off-the-shelf model and fine-tune it. With good data embeddings, we can easily find outliers just using nearest neighbors. So here I have a picture of, on the top right, image data set, fashion MNIST, with some outliers injected in it. We just injected outliers from MNIST. And here we can find those types of outliers. And I won't talk about, yes, this is such a simple approach. I won't talk about the details, but it turns out that this simple approach works quite well. And we've done extensive benchmarking on this. And then yeah, this algorithm is implemented in the CleanLab open source. What I'll talk about in a little bit more detail in this talk, the first category of label issue that we'll do a deep dive into is, the first category of data issue that we'll do a deep dive into is label issues. So this is actually the first type of data issue that the CleanLab open source focused on. And really, that was the origin of all the research we've been doing. We started with label issues about 10 years ago. And to address noisy labels in machine learning, training and test data, we developed a set of theory and algorithms called confident learning. And from this, we can get a whole lot of useful things we want to be able to do when we're dealing with noisy data. So we can do things like finding the mislabeled data, like label errors in a classification data set. We can not only flag the errors, but we can rank the data by likelihood of being a label error. So if you were to say, want to manually review the most valuable data to manually review, like I'm going to look at 1% of my data and I want to look at the stuff that's most likely to be wrong, we can use this set of algorithms for doing that to rank the data. Confident learning also lets you just do supervised learning with noisy labels. It's an approach for doing learning with noisy labels because you can just use the algorithms to flag all the label issues, throw them out, and do machine learning only on the clean data. So even without any human in the loop or data correction, you get an approach for doing supervised learning with noisy labels. And we can also use it to characterize label noise in a data set. So we can do things like tell how often any given class is mislabeled as another class. So say in our ImageNet data set, we can tell how frequently lions are mislabeled as tigers or lions are mislabeled as dishwashers. And this sort of an analysis can be really helpful for designing data ontologies. Like we might notice that two classes are very frequently mislabeled as each other, and say maybe merge those classes, or maybe give better instructions for annotators as to how to distinguish between those classes. So it can be really useful for the data curation process. And the key idea behind confident learning is that we can use any machine learning models out of sample predicted class probabilities to find label errors. Like we can just train an ML model on our data, and that can give us predictions, right? And then the interesting math behind confident learning helps us decide when to trust the ML model's predictions over the label and the data itself. And at a high level, we do this based on the machine learning model's confidence on that given data point, and then its confidence in average, like how often it, or what's its confidence for predicting any given class over the entire data set. And so I won't go into the mathematical details in this talk, but we've shown that this approach gives good theoretical guarantees under certain settings where you have certain distributions of label noise or things like that. And kind of aside from that, empirically validated that this works quite well. So I'll focus a little bit more on the empirical validation side in this talk. And so one thing we did was we benchmarked, or evaluated a bunch of these highly curated academic data sets and use these confident learning algorithms to automatically find label issues in them. And here we actually went a step further, and we took all the data points we found and flagged as label issues. We also looked at what was the predicted label given by the ML model, like what's the alternative label for any given data point. And then we had humans validate all the results we found. So we could filter out, say, like the 1% of data that's most likely to be wrong, and then we can check our results. So we can use this to both benchmark our technique, and we were able to actually get a little bit more flavor on the different types of label issues and how they might be corrected or how we might want to deal with them based on this analysis. So we had humans validate, given a data point and given the original label and an alternative label, whether or not they think the label for the data point should just be changed to the proposed label, whether both labels apply, whether neither label applies. And then there was also the case, since we had multiple annotators, where people just didn't agree with each other. So this gives us a classification of data points that are flagged to have label issues. And so looking at these one by one, we can look at the ones which annotators just fail to reach agreement on. Like looking at the leftmost one here from the MNIST data set. Yeah, that looks like potentially a 4, potentially a 9. Like it's just a kind of ambiguous or hard example. And the rest of the images in this category fall into that same classification. And so what you do with these really just depends on what these look like and what you're trying to do. Like maybe if you have hard examples which do indeed have a correct label, like you might want to augment these and supply more of them to your ML model so it does better on them. Or maybe you want to throw them out if they're just bad examples. We were also able to identify a bunch of data points that were just bogus data points. My favorite one here is the fourth column here from Caltech 256. So this is it's just like a mathematical graph of something that looks like a sigmoid function. It was labeled housefly. Not sure how that happened in that data set. The machine learning model predicted ladder. There was no mathematical graph or sigmoid function label in this data set. And so this is just a bogus example that in this particular case would probably be thrown out. This type of analysis also reveals a different type of issue. So we found in several of the image data sets, data points which have multiple labels that apply to them. Like this one from CFAR 100, this first image here. This is a picture of a hamster sitting in a cup, right? So this is kind of a limitation of the way we've set up the machine learning task. It's not really sensible to set this up as a single label classification task where the ML model has to predict a single label and we penalize it if it produces the wrong label when multiple labels might apply, right? So if we were to do this type of analysis and see a bunch of these multi-label data points, we might consider actually changing the way we've set up our ML task and changing it to a multi-label classification problem than a single label classification problem. And finally, we have just data points that were straight up mislabeled, like this data point from MNIST, which was labeled an 8, but is obviously a 9, or this thing that's obviously a frog, but was labeled cat in CFAR 10. And so these we can actually just correct the correct label, and we've improved our training data, and we're no longer confusing our model with bad data. On the learning with noisy labels side, what's kind of neat is that these confident learning methods, and in general, methods that are based on data-centric approaches that do basically training, but with the bad data removed or fixed, tend to do a lot better, especially in regimes with high label noise or certain types of label distributions, than older, more model-centric approaches, which focused on tweaking, say, the loss function or the model architecture or parameters to try to deal with noisy labels. So next, I'm going to talk a little bit about some of the Gen AI related applications of these algorithms of automated label error finding and associated techniques. So one common thing to do these days to train a high quality text related model is to take a base LLM and fine tune it for a particular task. So like this example here from the Stanford politeness data set, where we have some text and we want to classify it as impolite, polite, or neutral. And with LLM fine tuning, it's super powerful because we can actually just take a really tiny training data set for fine tuning and get a highly performant model out with limited money and time required. But one of the consequences of that, of using these tiny data sets, is that data quality really matters. It's like if they're incorrect data points, like this one that we were able to automatically identify in the Stanford politeness data set, it can harm model accuracy and it can have a pretty big impact, right? Like if you're only fine tuning with 100 examples or 1,000 examples, if you have 20 of those that are incorrect, you're really going to confuse your model. And so here, for example, we were able to benchmark this. We benchmarked a number of different LLMs on an original data set, and then we ran CleanLab and just threw out all the data points that were flagged to be erroneous. So we might have even thrown out things that were incorrectly flagged, right? And that alone improves performance. So that's this yellow bar shown in this graph. So original performance on the original data set across the 3 LLMs shown in this gray bar. If we just throw out the bad data, oftentimes it improves performance. And what we can do that's even better than throwing out bad data is actually improve the data set. So we can say have a human in the loop approach where we review the small subset of data that's flagged to be incorrect and correct the labels or throw out the data that's out of distribution. And yeah, as you would expect, that improves performance even more. So that's shown in the blue color here. And tying this back to what we talked about briefly several slides ago, yeah, how do we evaluate the performance of these models? So we can't just take the same noisy data set, like split it into a train and test distribution or test set, and then evaluate on the noisy test set, right? So in all of these experiments, we made sure to evaluate the model on high quality labeled data. So like we had multiple annotators, we used our approach to throw out the bad data and all that. So test data set quality is super important for benchmarking. And we were sure to follow that, follow good practices there when doing benchmarking of these kinds of experiments. And yeah, similar results across different data modalities, right? So here's another similar benchmark done on the student grades data set, where we trained a different ML model on the data, threw out the bad data, got better performance, but then actually fixed the bad data rather than throwing it out, got even better performance. That's a general pattern we find. And same detail here about evaluating the model accuracy on high quality labeled data. Another interesting Gen AI related application is RLHF. So OpenAI and others have talked about how reinforcement learning from human feedback has been one of the key techniques that's gotten models like ChatGPT to perform so well, right? And so part of that involves having humans provide annotations on prompt and completions. So you might set this up as, okay, you have a prompt and the model provides a couple different completions and the human picks the best one, and you'll use this to fine tune the model to produce annotations that, or completions that better match what humans prefer. And so we were able to take this anthropic RLHF data set. So that data set has this form of completion and then a chosen completion and rejected completion, and just use our label error finding techniques to actually find annotation issues in this data set. It's like the way we'd frame this as a label error finding problem is we'd have a prompt and a completion and a completion and just treat this as a data point and have the label be like, is prompt A or prompt B better? And that's framing it as a label error finding problem. And yeah, using that, we can find that, yeah, like this data point is detected as a label error and this completion is actually no good and this one's much better. And so we can use this to curate RLHF data sets. Another Gen AI related application, you might have a setting where you're trying to evaluate different prompts for your LLM, like whether you're doing zero-shot predictions or you're doing few-shot or whatever it is. You'll have different prompts you're using to evaluate your, or you're trying to evaluate different prompts to choose, say, one particular prompt you want to use in your production application. And so you have a big data set and you have a couple of candidate prompts and you want to find the best one. So what we found here is that, yeah, focus on the quality of that test set really matters. So if you don't have a high quality test set, you can have a situation where a prompt A performs better than a prompt B. So you get a higher accuracy with prompt A. But if we were to clean the test set, then prompt B actually works better. So if you were to just use a low quality test set, you'd be choosing the wrong prompt to use in a production setting. So again, yeah, emphasizes this need for focus on high quality, not only training data, but test data. Another Gen AI related application, you might be doing few-shot prompting for your LM, another really powerful technique, right? And so similar theme here, if we provide in our few-shot examples, incorrectly labeled data, that's going to harm the performance of the model and it's going to get confused and might produce incorrect results here. And so, we've done some benchmarking here too, and it's found that the data quality matters, and these automated data curation and quality approaches can help improve the results here. What's kind of neat is that we found that having, like, if you prompt the model and say, okay, here are a bunch of examples, some might be noisy, the model does okay, but it does much better if you have, even if you have fewer examples, but you only include the examples that you're very confident about. Like, having bad data is much worse than having just less data that's high quality. All right, so switching topics onto a different data quality and curation issue. I'm going to talk a little bit about handling data that's labeled by multiple annotators. Like, a really common way to label data for supervised learning is to start with unlabeled data and then have a bunch of human annotators label that data, right? And oftentimes you have multiple people label individual data points because people make mistakes. And so then there's some questions that arise once you have data that looks like that, where you have a data point along with multiple annotations on that data point from different humans. One thing obviously that you want to do is you want to determine a final label for a data point, like some kind of consensus label. And there are other quantities you might be interested in too, like determining how confident you are that the consensus label is correct. And furthermore, you might be interested in actually assigning scores or flagging bad data annotators. Maybe you want to get fewer annotations in the future from these bad annotators and get more annotations from the ones who are found to be good annotators. And so, making this a little bit more precise, we might be interested in determining consensus labels, aggregating the annotations from individual annotators, finding a quality score, a continuous score for each consensus label that measures how confident we are that that label is correct. And finally, we might want to measure or get a measure of the quality of each individual annotator. And so there are simple baseline approaches that you could use to do these things. Like, if I just asked you to come up with something, you might say, oh, let's do consensus labels via majority vote. But oftentimes these baseline methods either don't handle a corner case as well or just don't get great performance. We can actually do a lot better. And so we've done some research in this area as well and developed an algorithm called CleanLab. And some of the key ideas here are that there's actually a lot of information in the data itself, and we can actually use machine learning to help give us better results for these consensus label and quality scores that we're interested in. So what we can do is train a machine learning model on the data that we are trying to label. And we can treat the annotators kind of like we treat machine learning models. And how do we combine results from multiple machine learning models? Well, the standard approach there is ensembling. And so we do the same thing here. Like, we'll ensemble a machine learning model that we've trained on the data along with the predictions from the annotators to get the final results, the final consensus labels. And the interesting details in here are on how we weight the different annotators and how we weight the model. And we do this based on how we estimate the trustworthiness of each particular annotator and how that relates to what we estimate as the trustworthiness of the trained model. And this algorithm deals with a lot of the corner cases or tricky things that come up. Like, dealing with the variable number of annotations per example, or being able to do things like provide good results even when you have certain data points where there's just a single annotation, things like that. So again, not going to get into the mathematical details, but I'll present some of the high-level benchmark results from this. And this algorithm is implemented in our open source, so it's available for anybody to use today. So yeah, we went and benchmarked this on against other methods like the baseline majority vote, along with other methods that have been used in the past for doing things like determining consensus labels. The setup here was that we were benchmarking on the CFAR10H data set. So this is that CFAR10 image data set we saw a couple examples of from before, but researchers took this data set and then got a bunch of new annotations for it. So they had 10 annotators, and then every single image in here is labeled by these annotators, by some subset of them. So we have the gold labels from the original CFAR10 data set, and then the CFAR10H data set, which contains new annotations. And so we benchmarked CrowdLab, which is at the bottom in this stack here, against a couple of different methods, including the baseline majority vote, and found that it outperforms them in terms of having a higher accuracy in determining consensus labels as compared with the original labeling of CFAR10. And similarly for the other quantities we're interested in, like the score we assign on how confident we are that a given consensus label is correct, we're better calibrated there, and we're better calibrated in estimating annotator quality as well. And then one extension we've worked on of CrowdLab is something called ActiveLab. So this is dealing with multi-annotator labeling in the online setting. So you might have a setting where you want to get, say, the best machine learning model for a given data set, and you have, say, an unlabeled data set, you have a partially labeled data set, and you have some fixed annotation budget. And then the key question there is, what data point do you label next? Like, do you label, say, one of your unlabeled data points? Do you take one of the data points where you already have labels, but maybe you're unsure if that label is correct? What's going to improve model performance the most? And so ActiveLab is an extension of the CrowdLab quality score that we assign to data points. And then we use that same score to determine what data points to label next. And so here too, we're able to show through benchmarking that this is an effective method, both for more classical models and for neural networks. So we see in the purple line here, it's over a number of iterations of active learning. We're looking at model accuracy. And we see that for a given number of iterations, we outperform other methods. And if we look at what we converge to an overall higher accuracy using this approach compared to other methods, like a baseline, if we just randomly choose what data to label, or if we're doing it based on entropy or uncertainty. And so next, I'm going to talk a little bit about some case studies of some real-world applications of these data-centric AI techniques we've just been talking about. So CleanLab software, both the open source and our SaaS CleanLab Studio, are used by a whole bunch of companies for real applications. And here are some of the cool examples I want to highlight. So here's one of BBVA, which is a large financial institution, doing active learning with CleanLab. So what they were trying to do is they had this machine learning task where they were trying to categorize financial transactions for their online banking app. I'm sure many of you have seen something like this before. In your banking app, you have a financial transaction and you want to categorize it as, say, like dining or paycheck or rent or something like that. And so they're trying to train a machine learning model for this, and they're starting with annotated data. And they used CleanLab and in particular ActiveLab to implement this active learning loop. And they found that with a focus on like data curation and data quality, they were able to actually vastly reduce their labeling effort. Like they actually said that they were able to reduce their labeling effort by 98%. So huge cost cutting there. And even with way less data, they were actually able to improve model accuracy. So they said they were able to boost model accuracy by 28%. And I think this last bullet point makes it really clear that how powerful data-centric AI is. They were able to achieve this improvement in accuracy and reduction in costs without any change to the modeling code. So solely by focusing on the data, they were able to get this huge performance boost. Another application where CleanLab is used is it's used by Google to find and fix label issues in speech data. So they're improving the data used for training speech models, and they're also they're interested in quantifying annotator accuracy to figure out, like which annotator should be labeling more examples versus which annotators say need more training on how to do this task. And the techniques are also used for estimating error rates and wake word detections. Like when you say, okay, Google, they have a bunch of labeled data for training the model to detect that. And CleanLab is used as part of curating that data. And CleanLab is also used at Amazon and other big tech companies for similar tasks for these speech-related models. One final case study that I want to highlight is Berkeley Research Group. So this is a data consulting company, and they're using CleanLab for a number of projects. Here's one interesting one that they're using it for. So they're trying to, they were dealing with a task where they had a bunch of documents, and they were trying to determine whether or not the document is relevant to a given legal case. This was relevant in the discovery phase of these legal proceedings. And so the documents were a lot bigger than these little examples I put here, but they had documents and they were labeled like this is relevant to the case versus this is not relevant versus this is privileged information. And here too, so this data was originally labeled by lawyers. And so unlike say, some of the image data set labeling that we've looked at earlier, where say any person could label the data, like here we need really expensive lawyers to label this data set. And turns out that, yeah, lawyers are also human and they make mistakes. And so some of their data had errors in it. And so it's leading to, well, yeah, they just wanted high quality data to begin with. And this was a problem. And they're also trying to train machine learning models on the data, and that was harming model accuracy. And so they used CleanLab, and BRG actually used our SaaS tool rather than the open source. And they were able to improve the quality of their data set and improve model accuracy by 15% and reduce the amount of time they were spending on data verification and training iterations by 1/3. And another kind of interesting thing in this case is that they really wanted this automated analysis of the data. Like for their application, it was very valuable to not have a human look through all the data and say, oh, I think this is wrong, but to have an automated tool flag the data. It's a more objective way to assess data quality. So, giving a little bit of a summary of what we've worked on, we've been doing research in this area of data-centric AI for quite a while, and all the work we do originates in fundamental ML research that we do. Like we do research, we do benchmarking, and then we turn a lot of what we do into open source. So I think basically everything I've talked about today has been open sourced in this github.com/cleanlab/cleanlab package. And then one final thing I'll talk about before summarizing is this one application we're focused on right now that I think is very exciting and interesting. So we're thinking a lot about data quality for text generation in LLMs. I'm sure you've heard about this in the news or other places, that one of the biggest problems with large language models is hallucinations or bad outputs. And so here we can see some examples of inputs and outputs from an LLM that's trained to do, that we're tasking to do some type of customer service task. And if you were to just deploy a model that behaves like this, it's like let it loose on customers, that would be kind of bad, right? Like sometimes it does well and gives a good answer to the user, but in other cases, it just behaves in this undesirable way. And yeah, how do we prevent this sort of behavior, or how do we at least identify when it's operating in this good regime versus this bad one? So one area where we're starting out is focusing on question and answer for things like just factual question answer pairs. And so, yeah, again, same pattern as the previous slide. So we tried asking a bunch of questions to an LLM like GPT-4. Actually, this might have been against GPT 3.5, but yeah, these are real input-output pairs from some LLM. And we find that if we ask questions like, okay, what is 100 plus 300? It gives us a correct answer. If we ask, yeah, here's some other math question, it gives us a wrong answer. Some question about Jerome Powell, correct answer. Some other question about Jerome Powell, incorrect answer. And so in the absence of any other output from the LLM, we just, like, how do we know when it's correct versus when it's not? Wouldn't it be wonderful if it could provide some sort of a score, similar to how the other CleanLab tools provide scores, like label issues and other things, to indicate how uncertain or how confident the model is in its outputs? And so this is something we've been working on, and we've released the CleanLab Trustworthy Language Model. And so these are, again, real inputs and outputs from that TLM. And we've shown through benchmarking that this provides good results. Like it does indeed, LLMs are not perfect. It sometimes produce incorrect answers, but when it does, it gives a low confidence score. And so you can imagine how this could be helpful in any downstream application. Like say you use this in your customer service setting, and the LLM can handle a bunch of the queries because it's confident in them, but in say some small fraction of the queries it's not confident, it gives a low confidence score, and you can build the surrounding system so that when you have the low confidence score, maybe you just bail out and give the query to a human to deal with. I can give a brief overview of how this works. So this is something you can actually use today. So if you're interested in signing up, just go to cleanlab.ai and you can sign up for the TLM. But some of the ideas behind the implementation of this is we actually use language models for estimating their own uncertainty. And so a couple of things we do, we take the original question answer pair and we can feed it to the LLM a bunch of different times and get a number of outputs. Like these are randomized algorithms, you can do sampling. And with a bunch of different outputs, then we can compare the different outputs from the LLM against the original answer. And one intuition there is that if the LLM often gives the same or like similar outputs, then it's pretty confident in what it's outputting. But if you get like high variance there, then it's less confident. And then another technique we can use, we found that LLMs are pretty good about reasoning about their own outputs. So we can actually automatically craft prompts that ask the LLM to analyze its own output. So we give it a prompt, a question, and then the answer that was originally given by the LLM. And we instruct it to reason about its own output and determine whether or not, like whether it was correct or it was incorrect or if it's just not sure. And this can give us yet another score that can help indicate the confidence of the LLM. And all of these feed into a final confidence score. There's some details there on how we weight these different things and how we compute them. But at the end of the day, we can use this technique to get a confidence score. And when we find through benchmarking on question answer data sets that we get good performance in terms of giving a high confidence when the answer is correct and giving a low confidence when the answer is incorrect. So that's one of the things we're up to right now in terms of new developments that are coming out of CleanLab. And finally, taking a step back and just looking at the ML solution landscape, if you look at the tools that are out there, when you start out, okay, you have a data set, you want to collect initial labels. There are a lot of tools out there for doing the initial data labeling and crowdsourcing. They're like ETL and data transformation tools for storing data, like data warehousing solutions. So it gets you data, but it's often unreliable data. It's lower in quality that you want than what you want. And then at the end of the day, what you want is a reliable ML model, right? So you want a deployed model that works well on your use case. And there are a lot of solutions out there for training ML models, like lots of open source tools and SaaS solutions as well. But how do you get from unreliable data to reliable models? So this is where CleanLab comes in. We're all about helping you get from raw data to then using AI to improve your data, doing automated data correction to give you a better data set that you can then use for better AI or whatever task you're using your data for. And most of this talk was focused on algorithms in the CleanLab open source. I thought that's what would be most interesting to this group of data scientists here. But we also have a SaaS tool. And the reason we built this is we found that fixing data, not just finding the issues in data, but fixing data really benefits from an interface. So one of the main things that our SaaS tool provides is this interface for looking at the analysis results that the open source can also provide and actually going through and making the corrections. And then a second thing that it provides is the AI to actually detect the issues. Like what I talked about in this talk relies on embeddings and predprobs and like correctly computed out of sample predicted probabilities from your ML models. But what we've done in CleanLab Studio is automated all of that. So it's really just drop in a data set and then some magic happens at a high level, run AutoML and then all the open source and some new things that we've built that are only in Studio to give analysis results. And then it provides this interface for reviewing and actually correcting these issues. So you can use whatever human in the loop approach is, review a small fraction of the data to most effectively spend time and annotation budget to get a high quality curated data set at the end of the day. And we have a lot of automation in here as well. Like we have this magical auto fix top issues button that can automatically curate your data for you. So that's the talk. Covered a bunch of algorithms on data-centric AI, why we think DCAI is interesting. A lot of this is available in the CleanLab open source package, which you can just use today. And if you're interested in Studio, you can sign up for that as well. And I'm happy to take any questions.
Thank you. So many interesting ideas in there. Don't know where to start with the questions, but I saw there was one detailed question in the chat at some point asking about one of the figures. Can you see it in the chat?
Yes.
I'm afraid I can't remember which figure it was anymore, but
it was one of the early ones about yeah,
These?
it was this one, yeah.
Yeah, so here what we did was we took the original noisy data set, that's the gray, but then we ran CleanLab, and what the tool does is it flags a bunch of data points that are potentially erroneous, that are potentially mislabeled, and we just threw them out. That's the yellow bar. So we trained on a smaller data set. So what we did here is, in the blue bar, we used CleanLab Studio and then actually reviewed the data points that were flagged as incorrect. CleanLab Studio suggests a correct label for those, and we either accepted it or rejected it for the fraction of data that was flagged as being erroneous. And so rather than just having a smaller data set, we had an improved data set that was nearly as large as the original. So only the bad was like outliers thrown out, but then all the other mislabeled data points corrected.
Okay. Can I ask another question?
Yeah.
I'm wondering, have you studied like what factors and what parameters matter the most in order for your methods to be most effective?
Yes and no. So we've proven some theoretical guarantees, like under what types of noise distributions can we exactly find all the label issues. So those results are in the paper, and I can link the specific paper in the chat in a moment. But aside from that, we've just done a lot of benchmarking, because I think there's just a gap between the theoretical assumptions and just like what real world data and noise looks like. And so we found it works pretty well, but on real life data, there's no guarantees, and if it doesn't perfectly match the assumptions made for the mathematical proofs.
Other questions? Meanwhile, like when does this break down? Like how much noise can you tolerate in the labels before it sort of breaks down? Is it possible to quantify
I think
that?
at a high level more than you think. So this is also covered in this paper I just linked. And I think one of the results I presented in the slides was with 40% label noise. So we can actually tolerate quite high proportions of noise. Kind of as long as there's any signal in there, we can extract something useful from that signal. Now, of course, if you just take a randomly labeled data set and throw it into the tool, it's not going to give you anything useful back. But you can get surprisingly far with it on even highly noisy data.
Cool. So what about, I guess this is probably also data set dependent, but like do you have the sense that this works well on longer texts as well? If you're doing text classification, for instance, like big chunks of text, as opposed to these shorter messages that were shown in this presentation?
Yeah, so the short messages were there because I can't fit documents into the slide that easily. Yeah, so we're actually working with some customers right now that have just PDF documents of pages and pages long. So yeah, the same techniques can work there.
Okay, interesting.
Yeah, there are a number of approaches to use there. One is we can actually just use the huge chunks of text, and that works just fine. We've also done some things where we individually analyze pages rather than the entire chunk, rather than the entire document. It really depends on the application. We've had some settings where it actually doesn't matter what's in the entire document, like the first page is predictive enough, so we can actually truncate it. Yeah, 3 different approaches we use.
And a similar kind of question again. I suspect this is probably like really data set dependent, but is there any sense that this technique is working better for a certain type of data, like images, text, tabular, or it's just completely dependent on the data set?
Yeah, it's just dependent on the data set. For sure, there's settings where it doesn't work quite as well as others. Another thing is, so going a little bit beyond what I showed in the slides here, in CleanLab Studio, we're doing some fancier stuff. So we're training a whole bunch of models from scratch on data, but we're also using foundation models. And so there we can get, like, thanks to the foundation models, we can get really good performance on like really noisy data if it's something that the foundation model's seen before, right? So like, say you're doing like text classification, like politeness classification, you could throw in a garbage data set, and since the foundation model like more or less understands it, get good results out, so it just kind of automatically work itself out. On the other hand, if you try with a really low quality data set with data that is not in distribution for the foundation model, so like that foundation model's contribution isn't as high, and the models we trained from scratch don't do as well because the data is really bad, then the performance can be worse. So imagine, for example, an image data set of cats and dogs where the labels are really low quality. The tool will still work well because the foundation model's seen images of cats and dogs. It already knows what they are. On the other hand, if you have a manufacturing like defect detection data set, say, which might not be something that the foundation model has been trained on, and all the models we trained from scratch are trained on this low quality data set, then it might not work as well.
Okay. Other questions? Anyone?
Well, I don't have a question, but I have a success story, if you will, regarding this. And we used well, some LLM to generate synthetic training data for sentiment analysis. And then there's two questions. One is, can we trust the labels to train our downstream models on it? And the other one is if the data generated is similar enough for us to use. So I mean, we could trust the labels since we just discarded anything that CleanLab flagged as weird in some way. So in that case, it really helped us. And we use both the open source model as well as the studio version of it. Thanks.
Have you had any cool applications in biology or medicine? Just curious.
Yeah, if you look on Google Scholar, there's a number of medical or bio-related research papers where they've curated their data using the CleanLab open source. We haven't had as many other people in the like med tech space use CleanLab Studio yet. That's something we're working towards.
Yeah, I mean, for sure, there's a lot of noisy data in those domains, so could be a good place.
Yeah.
All right, but if there are no more questions, I think we should thank Anish for this super interesting, information-packed presentation. And yeah, those of us on this side of the Atlantic are going into the weekend soon. Hope you'll have a nice weekend as well, Anish.
Yeah. Thanks for having me, Mikhail.